Good morning. So in the last class, I have completed the design of combined footing. So today, let me take up the next topic, that is the portal frame. Okay. So what is that portal frame? So in a building, you people know that, so there will be a footing. Okay. Soon after that, there will be a column. Next, there will be a beam. Above the beam or monolithically casted with the beam, there will be slab. Okay. So now I will be explaining what is the portal frame. First, have an idea. So what are all the different structural components of the building? So one is the slab, next is the beam, then is the column, then is the footing. Now, what is that portal frame? The footing, column and the beam, these three combinedly called as the portal frame. Okay. So will not include slab in the portal frame, but if we want to design the portal frame, we need to know what is the load that is coming from the slab. Okay. So portal frame means it is the footing, it is the column and it is the beam. These three parts, they are combinedly called as the portal frame. Okay. So now, as per your syllabus, portal frame is of two types. Okay. One is the fixed portal frame and one more is the hinged portal frame. Okay. So based on the fixity at the bottom of the support. Okay. If it is fixed, we call it as fixed portal frame, and if it is hinged, we call it as hinged portal frame. Okay. So usually wherever we generally see the construction, it's all of the fixed portal frame type. So then where we will be using the hinged portal frame? Okay. It's just a support, that's it. Fixed support, hinged support, that's it. Okay. So where we will be usually going with the hinged support? Usually in the bridges. Okay. So usually we provide the roller support and one more side we go with the hinge support, or in the earthquake prone areas where if it is fixed support, what will happen? Whenever an horizontal load hits the building, so the fixed support won't allow the building to sway a little bit. So what happens? There might be a chance of cracks. So whenever it is hinged, there is a chance of a little bit flexibility. So that's why in such cases we provided with the hinged portal frame. So now let me take up the fixed portal frame. Usually in the examination, if they ask you people the theory part, so explain the different types of portal frame. So you can explain, the first one is the fixed portal frame and the second one is the hinged portal frame. Okay. So now let me take up the first one, that is fixed portal frame. Okay. So let me directly take up a design problem. Okay. Let me write that. A hall of dimension 8 meter wide and 20 meter length consists of number of portal frames, number of portal frames at every 4 meter, center to center. The height of the portal frame up to the center of the beam, is 5 meter. Next, the live load on the floor is 3 kilonewton per meter square. 3 kilonewton per meter square, and floor finish. and floor finish. So, and floor finish is 1 kilonewton per meter square. Use M20 grade concrete. Use M20 grade concrete and Fe415 and Fe415 grade steel. 415 grade steel. Design the following component. Design the following component. Design the following components of fixed portal frame. Fixed portal frame. First one, slab. Second one, beams. Third one, column. Fourth one, it's the footing. They have given one more information, that is, take SBC of soil is equal to 120 kilonewton per meter square. 120 kilonewton per meter square. Okay. So, this is the question that I will be taking to make you people understand the design of fixed portal frame. So, let me read it again. A hall of dimension 8 meter wide and 20 meter length, okay, consists of number of portal frames at every 4 meter center to center. Every 4 meter center to center. The height of the portal frame up to the center of the beam is 5 meter. The live load on the floor is 3 kilonewton per meter square and the floor finish is 1 kilonewton per meter square. Okay. Use M20 grade concrete and Fe415 grade steel. Design the following component of the fixed portal frame. Okay. In the exam, if they ask for hinged portal frame, please be careful with this. Even though in the question, if they have mentioned hinged and if by mistake, if you people have done the fixed portal frame, then the value will changes. Procedure is same. I will be explaining that a little bit later. Okay. So, now let me enter into the design part. Okay. So, now let me briefly explain you people what is this question. So, they are telling a hall of dimension 8 meter wide into 20 meter length. 8 meter wide into 20 meter length. 8 meter wide into 20 meter length. Okay, this is 8 meter and this is 20 meter, they have told. Okay, consists of number of portal frames at every 4 meter center to center. Observe here. I think in the buildings you people might have seen this. So, there will be a portal frame. What do you mean by that? A column and a beam and footing will be at the bottom. Okay. So, column, beam. So, one more column. So, this is combinedly called as one portal frame. So, obviously at certain distance there will be one more column, one more beam and one more column. Okay. So, the span between these two portal frames, okay, is particularly called as one span of the portal frame. Like that, what is the span of the center to center of the portal frame that they have given in this question? So, it is 4 meter center to center. It means that I do not know what is the size of the column and all. Obviously, column will be there. I do not know the size. So, let me write it like this. So, please remember. So, total is 20 meter. At every 4 meter there is a portal frame, means at every 4 meter there should be a column. So, 4 meter, 8 meter, I mean this is also 4, totally I am counting 4 meter, 8 meter, 12 meter, next 16 meter. Okay, the final one is the 20th one, 20 meter. So this is how it has been placed. Center to center I am taking. So center to center, they have given it as 4 meter. So they have given it as 4 meter. So please remember this. So obviously whenever there is a portal frame, so I need to mention the beams. So whenever it's a portal frame, I need to mention the beams. So this is how the diagram look like. So it's a big hall. Okay, so at frequent intervals they have provided the portal frame. Okay, so now while designing, let me not consider the entire thing. Okay, let me consider the span, first span. Okay, only let me consider this. So now if I design it for this, don't you think that all the other spans are same? So please remember, so I will be designing the slab as one-way continuous slab. I will be designing the slab as one-way continuous slab. I think in your 5th semester in design of RC structural element, while studying the slab portion, you people know there is one-way slab, there is two-way slab, there is one-way continuous slab. So here, as there are frequent number of slabs, there are many number of slabs at frequent intervals. Okay, so I need to design this as the one-way continuous slab. Anything? Any doubts here? So now I will be proceeding further. So keep this diagram in your mind. So keeping this diagram in our mind, let me start the design part. Let me rub this. First I will be going with the design of slab. Sir, in the starting of the class you told that slab should not be included in the portal frame. Obviously we should not include it, but the thing is, if you want to design the portal frame, you should know what is the load that is coming from the slab. Yes or no? Because whatever the load that is coming from the slab needs to be taken care by the beam, from the beam to the column to the footing, and then to the footing to the surrounding soil. So that's why slab design needs to be done. Okay, so let me proceed further. So now first step, as usual, it is the data part. So what are all the data that they have given? So they have given M20 grade concrete. What do you mean by M20 grade? So it is nothing but FCK. It's 20 Newton per mm square. Okay, then they have given the grade of steel, FY. So it's 415 Newton per mm square. Okay, so next they have given the SBC of the soil. So I think it's 120, I guess. So yes, it's 120 kilonewton per meter square. So next, anything else that they have given? So height of the column, live load they have given, floor finish they have given. So live load, it's 3 kilonewton per meter square. Floor finish, so floor finish also they have given. So that is 1 kilonewton per meter square. So now let me enter into the design of one-way continuous slab. So the second step is, let me directly enter into the design of one-way continuous slab. Design of one-way continuous slab. So now the general design procedure. What is the general design procedure? So as it is a slab, finally what I want? I want the spacing of bars. If I want the spacing of bars, I want to know the area of steel. How much area of steel you need to provide? How much it bends, that is the bending moment. How much it bends, what is the load that you are applying? So first I need to calculate, so load. Along with that, let me also calculate the dimension, because without dimension I can't calculate the load. So first let me start with the dimension. Okay, so let me go with this. So what are all the things that they have given? They have given the span of slab. Now be careful now. Don't consider the span as 20 meter. Don't consider the span as 20 meter. Just consider one particular span. So 8 meter by 4 meter. Okay, you people have already studied in the 5th semester. Okay, so whichever the shorter span is there, so in that particular direction the more load get transferred. So this will be the span, 4 meter. So what is the span of the slab? So it's 4 meter that they have given. So next I need to go with the dimensions. So this is the second one. In this, the first one is the dimension of the slab. We know what is the length and what is the breadth. Okay, so span is 4 meter, breadth is 8 meter. I am in need of the thickness. So how to calculate the thickness? So we have a formula. So what is that? I think you people know L by D ratio. So page 37 of IES 456. Okay, so what they have mentioned there? So for different beam, simply supported beam, cantilever beam, continuous. So like that, beam or slab, both. Okay, so here it's a continuous. So for continuous slab, the L by D ratio, they have given it as 26. They have given it as 26. And one more thing that they mention is, depending on the area and stress of steel for tension reinforcement, the values in A or B shall be modified by multiplying it with the modification factor obtained as per figure 4. I don't know anything about this, yes or no, because we are still in the starting stage of the design problem. So one thing is sure, we need to multiply it with the modification factor. But the thing is, to calculate the modification factor, I don't know any particular, I don't know any values here. So for time being, we'll do the assumptions. Finally, we'll do the check for each and everything. If it is not safe, we'll come back and we'll redesign. Okay, so now what I will be doing is, I know the span. So what is the span? So 4 meter. So can I write it as 4000 mm divided by, I want the depth only, effective depth. So is equal to, I don't know the multiplication factor. For time being, try to assume it as 1.2, 1.25, somewhere around that. So let me assume it as 1.25. So finally, so it's 4000 divided by D is equal to 26 into 1.5, that is 32.5. So finally, the value of D that we obtained here is 123.07. Can I approximately take this as 125 mm, that is 5 inches? Any problem? Once again I am telling, so these are all some assumptions that I have made. Okay, so what I need to do further? Obviously I will be doing the check for all these things. If it is not safe, we'll redesign. Okay, so no need to worry. Now, usually for slabs, and the span is 4 meter approximately, so it is 13 feet or 14 feet. So it's not a too huge span. So what I will be doing is, let me assume the dia of the bar for the slab. Okay, let me assume usually for a slab, main distribution bar I will be going with 10 mm. So sorry, main bars I will be going with 10 mm, distribution bar I will be going with 8 mm. So now let me assume that I will be using 10 mm dia bar, assuming 10 mm dia bars, Observe here, I want to calculate the overall depth, yes or no? Overall depth of the slab. overall depth of the slab. So observe here. So I know the effective depth. Effective depth means what? If I consider the cross section of the slab from the top of the slab till the center of the reinforcement of the slab, that is called as the effective depth. What is the effective depth? 125 plus. Okay. Next, I want to calculate the effective cover. How to calculate the effective cover? Observe here. It's nothing but half the dia of the bar plus, usually for slab we'll go with 20 mm clear cover. So 20 mm. Okay. So what is the overall depth? So don't you think that it's 150 mm? So now we have calculated the effective depth as well as the overall depth of the slab. Now after calculating the dimensions, so we need to go with the load. After load, it's the moment. After moment, area of steel. After area of steel, spacing of bars. So now let me go with the load calculation. Done. So next heading, let me rub this because I need the diagram for a while. Later on I will be rubbing the diagram. So now let me go with the load calculations. Okay. So now under the second step, which one is that? Design of one-way continuous slab. So I will be going with the load calculation. Load calculation. I want you people to think. Okay. So now what are all the load that will come on the slab? In general we'll think. Okay. So now as I am standing on a slab, okay, the first and the foremost thing is the dead load. Okay. So first I need to calculate what is the dead load of the slab. Next, what is the live load that is coming on the slab? Next, floor finish. All those things I need to consider. Yes or no? But here please remember, as it is a one-way continuous slab, the procedure is slightly different. Okay. So we need to calculate the dead load separately. We need to calculate the live load separately because the code gives the formula for different values. Okay. For dead load, they give separate value. I mean separate formula. For live load, they give separate formula, especially for one-way continuous slab. So what I will be doing here is, so let me calculate what is the dead load that is coming on the slab. So dead load of slab. Dead load of slab. So how to calculate the dead load of slab? Please remember, so the dead load of the slab will be given in kilonewton per meter square. Okay. So we know that dead load of the slab means density of concrete. Density of concrete kilonewton per meter cube. I want it in kilonewton per meter square into thickness of the slab into thickness of the slab. So please remember, so even after your completion of BE, if someone comes and asks you people how to design a building, so this is the procedure that we need to usually follow. So this will help you a lot in your future. Okay. So dead load of the slab is equal to density of concrete into thickness of the slab. So what is the density of concrete? We usually consider it's 25 kilonewton per meter cube into. So what is the thickness of the slab? Just now we have calculated. So don't you think that it's 150 mm in terms of meter? It's 0.15 meter. So after solving this, the value that we are getting is 3.75 kilonewton per meter square. So just 1 minute back I told you people, calculate the dead load separately, live load separately. So don't you think that floor finish also comes into dead load? So floor finish they have only given. So floor finish, so 1 kilonewton per meter square. So they have only given. So adding these two, the value that I will be getting is 4.75 kilonewton per meter square. So I want to design this. I want the ultimate load. So ultimate dead load. So ultimate dead load, ultimate dead load. I will be calling that as WG. Okay, so it's nothing but 1.5 into 4.75. So what is the value that we are getting? So it's 7.125 kilonewton per meter square. 7.125 kilonewton per meter square. So this value is WG. This is very important. So now I have calculated the dead load separately. Now let me calculate the live load. Okay, so live load that is coming on the building, they have only given, but we'll do one thing. Directly let me write ultimate live load, ultimate live load. So I will be calling that as WQ. So it's 1.5 into, so what is the value of live load that they have given in the question? It's 3. Don't you think that? It's 4.5 kilonewton per meter square. 4.5 kilonewton per meter square. Any doubts still here? Okay, so any doubts? Now I will be going further. So what is that? I have calculated the load. So what are all the load that are coming on the structure? So soon after calculation of load, what I need to do? So I need to calculate the bending moment. Okay, so now we'll go with page 12 of IS 456. So there they have given some values. Observe here. I will be giving you people an idea how I will be taking the bending moment. Observe here. Okay, this is the top view of the plan. If I see it in this direction, let me think that you people are standing over here and you people are seeing it in this direction. Don't you think that? It looks like this. Actually the span are same 4 meter, but as I have not drawn to scale, so the spans are at different positions. That's it. Okay, but actually they are 4 meter center to center. So now the thing is, observe. I think you people know the deflection pattern. Okay, so as it is a continuous beam, don't you think that the pattern will be like this? Yes or no? So please remember, here the reinforcement needs to be at the center. I need to give the reinforcement towards the bottom. At the supports, I need to give it towards the top. So, and one more thing is, observe, this is called as the end span. Okay, this is called as the interior span. So I need to concentrate. So end span and interior span, both I need to concentrate. Because if I consider only this, so at the middle the bending moment might be different. If I consider only the middle one, support will be different. So what I will be doing, the code only takes care of all those things. So the formula they have suggested in such a manner that each and everything will be taking care in that. Observe here, if I consider this particular span, okay, this is called as the end supports. In end supports, code says mid of the span and support span. Okay, in mid span, if they consider, okay, here also they consider the mid span as well as the supports. So page 12, so I will be writing that. So next it's the bending moment calculation. Next it's the bending moment calculation. I need the diagram, let the diagram be as it is. Okay, so now let me go with the next heading, bending moment calculation. Bending moment calculation. So for that, in the code only they have given. So from table 12, I made a mistake there. It's not page 12, it's table 12 of page 36. Table 12 of page 36. It's table 12 of page 36, not page 12, it's table 12 of page 36, IS 456. So there is a tabular column. As you people have already studied in 5th semester, so you people can go through it. So directly let me take up the formula. Okay. So the first one, we call it as the span moments. Span moments. Span moments means the interior span I am considering. The interior span I am considering. In interior span also, I will be dividing that into two types. So what is that? So it's the middle of the, span moments, yes. So middle of the end span. So it's middle of end span. Okay, so at the middle, what will be there? So they have given a formula, M is equal to, it's WG L square by 12, WG L square by 12 plus WQ L square by 10. Not WQ, there also it's W, just a minute, yes, it's WQ L square by 10. So let us substitute the value. WG we have calculated 7.125 into L square is 4 square divided by 12 plus WQ is 4.5 into 4 square divided by 10. So the final value that we get here is 16.7 kilonewton meter. Kilonewton meter. So similarly, we'll go with the middle of interior span. So middle of end span, we have considered middle of interior span. Please remember, in the end span, middle they have considered. In the mid span, middle they have considered. So next, it's the middle of interior span. It's the middle of interior span. It's the middle of interior span. So for that also they have given a formula, M is equal to WG L square by 16 plus WQ L square by 12. Let me substitute the value. So it's 7.125 into 4 square divided by 12, not 12, 16 plus 4.5 into 4 square divided by 12. So the value for this is 13.13 kilonewton meter. Similarly, let me rub this only. Okay. So next it is the support moments. Let me make this as B. So it's support moments. Okay. Here also next to the end support, next to the end supports, next to the end supports, observe here. So one thing is sure, it's a support moment. So support, near the support, not at the midspan, near the support. And that there also end support, near the end of the support means this. Okay. So here also they have given a formula. So next to the end support, it's WG L square by 10 minus WQ L square by 9. WQ L square by 9. Instead of writing it again, I am just altering it here. So 9. So what is the value that we get after substituting it here? And one more thing, it's not this, this is also negative. Please be careful. So if you go through the IS 456, you will come to know. Okay. So now what is the value that we are getting here? So it's minus 19.4. Minus 19.4 kilonewton meter. Similarly, next it is the other interior supports. Other interior supports. Other interior supports. So the formula for that is minus WG L square by 12 minus WG L square by 12 minus WQ L square by 9 minus WQ L square by 9. So here also minus, instead of 16 it is 12, here also it is minus, instead of 9 it is sorry, instead of 12 it is 9. Okay. So after solving this we get minus 17.5 kilonewton meter, minus 17.5 kilonewton meter. Okay. So now we have calculated the bending moments. Yes or no? We have calculated the bending moments. Now we'll do a check. Whatever the effective depth that we have given, is it sufficient for the bending moment? So that I will be doing it in the next class. So for time being, we'll wind up. Thank you.